So in this segment, we resume our prog3.s discussion from where we left off in the prior segment. And I've added a register diagram showing just the registers we'll use with R0 and R1 already having the values 2057 and -200 from the work done by lines 15 through 17, which of course we discussed in the prior segment. Now the next job is to get the value 2097 into R3 by translating the string of digits 2097 into an equivalent integer. This requires a lot of code, all of lines 19 through 32. And be sure you see the difference between 5 bytes containing the ASCII codes 50, 48, 57, 55, and 0, and the 32-bit binary pattern shown here in the transcript that is 2097. Conversion from humanly readable sequences of ASCII digits to the binary integer form is a common operation, and it's usually done automatically by I/O libraries, for instance C's scanf function. But you should understand the logic of this conversion, and its implementation in prog3.s illustrates several important assembly concepts. Lines 19 through 32 loop through each ASCII code in LdrStr one at a time. They build the binary equivalent or the equivalent binary value in R3, adding a new digits value each time through the loop. So what we'll see is that as we progress through the loop, R3 will first hold 2, then 20, then 209, and finally 2097. So lines 19 through 20 start the process by setting R3 to 0 and then loading R1 with the address represented by the label LdrStr. Recall from the end of the prior segment that line 20 does this via a pseudo instruction, which is really a PC relative LDR of the value at LdrStr loc. R1 thus starts with the value of the 2 in LdrStr, and we agreed in the earlier segment that this would be 4 if the program starts at address 0. And I'll also put the 0 that we're starting with in R3 there. The loop will use R1 as an address register to get each ASCII code in the sequence, and will advance it 1 byte at a time through that sequence. And so we come to our first in-lecture question. Storing the value of label LdrStr just so we can load it into a register, storing it at LdrStr loc of course, seems too complex. Couldn't we just write LDR1 or R1 LdrStr? Or maybe move R1 LdrStr? Why not? This is a bit of a review question. So recall again that an address is a 32-bit value, and it can't fit into a machine language instruction as a constant along with the opcode and register number and so forth. Also, LDR is designed to copy from memory, so anything it loads must come from memory, even if it's an address. By contrast, however, the move on line 22 can copy the constant 10 straight into R4, since 10 is a small value that fits into a move instruction. So, now we're ready to process each ASCII code in the string. At line 25, the top of the loop, we load the ASCII code at the address given by offset register R1. But there are 2 more new concepts on that line. First, we can adjust the LDR instruction to load just a byte from memory, not a whole word, by adding B after LDR. An LDR-B instruction loads the byte into the bottom byte of the target register, R2 in our case, leaving the other bytes 0. The addition of B tells the assembler to set a special bit in the LDR instruction, which tells the CPU to load 1 byte. Similarly, strb stores the bottom byte from a register into memory. And you can also load or store a half word, 2 bytes, by adding H to get LDRH or strH. The LDRB and strb instructions allow any address alignment without bus error. No need to be divisible by 4. To be technically exact, what they do is adjust the address to be divisible by 4, load the entire word in question, and then fish out the desired byte. So that's concept 1. Concept 2 is that we added a #1 after the bracketed address register, not inside the brackets. This is an auto increment. It tells the LDR instruction to increase the value in R1 by 1 after the load is done, thus leaving R1 holding the address of the next ASCII code, 5, or the address of the 0, for the next time through the loop. And I've adjusted the diagram accordingly. It's often convenient to steadily advance an address register through a range of values in memory, and the auto increment feature of LDR makes that easy without needing an additional add instruction. It works for STR too, by the way. The effect is similar to C's ++ operator. Line 25 effectively does an R1++. The increment can be larger than 1, as high as 2047 in fact, and it can be negative, as low as -2048. And this is because it uses the address offset bits in the instruction, which are unused otherwise on line 25. You can even do an address offset and an auto increment at the same time in the same LDR instruction. For instance, if we write instead, writing LDR R4, R5 #4 with an exclamation point after the bracket. This both offsets from R5 by 4 bytes and also increases R5 by 4. You can think of the bang as meaning make this offset stick in the register. It's like a C pre-increment operation, ++R5. So, question 2. To be clear, what is the difference between LDR R4, R5 #4 bang, as I have here, instruction LDR R4 bracket R5, #R4? What different effect, if any, do they have on R5, and what different effect on the value loaded? And the answer here is that the effect on R5 is the same. Both will increment it by 4. But the first LDR loads from the incremented address, and the second loads from the original address. Okay, let's move on to multiplication here. Once an ASCII code byte is loaded into R2, then lines 26 and 27 compare the ASCII code to 0 to see if we've reached the end of the string. They jump past the end of the loop all the way down to all done down here, if so. Note, by the way, that the 0 digit in the middle of the string will not trigger this jump, since it has the ASCII code value 48, not 0. Line 28 subtracts 48 from the ASCII code in register 2, leaving the numerical value of the digit in R2. So e.g. 0 if the code was quote 0, 1 if it was quote 1. And in fact, the code was 2, and we had ASCII code 50, and so subtracting 48 will leave us with just the value 2. Now we need to multiply the current R3 value by 10, and then add in the new digit's value. R3 is going to be our running total. For instance, if R3 were 20 and the next digit is 9, we need to multiply R3 by 10 to get 200, and then we'd add in the 9, arriving at 209. At present it's 0, so it'll be a no-op, but let's at least be sure how it will work when we do have a non-zero value in there. The multiplication can be done with a mul instruction right here. The ARMAssembly has several integer multiplication instructions. Mul, probably the simplest, does a simple multiplication of 2 registers. In our case, it's R3 and R4 that are being multiplied together, and then the result is saved into the first register, R5. So, in effect, the multiplication does, as the comment indicates, a multiply of R3 times 10, which is in R4, and puts the result in R5. Mul, unlike sub or add, can only be given registers for its operands, never constant values. And this is the reason that we moved a 10 into R4 and then used R4. The add instruction on line 30 then adds R2 to that multiplied result, completing the operation. Now, somewhat remarkably, that 2-step multiply and add can actually be done with a single instruction, MLA, multiply and add. This instruction takes no fewer than 4 registers. As the comment indicates, MLA computes a product of the second and third registers, adds in the fourth, and then places the entire result back into the first register, R2 in our case. But it has some interesting restrictions. First, like mul, it works only with registers, not constant values. And that's again why we put a 10 into R4 instead of just writing 10 as a constant in the MLA instruction. And at least on older ARM processors, the first and second registers cannot be the same due to subtle hardware design issues. And that's why we put the result into R2 and then on the next line copy it into R3. Okay, that completes the loop, and the B to loop top, as we already know, is our way of doing a while loop and jumping back up for the next iteration. Now, once the loop exits at all done, R3 will hold 2097. And that is the binary value, not the text string. And R0 already contains val b minus 200, or 2057. So the subtraction on line 28 leaves 2097 minus the val b minus 200 difference, or 40 in R3 when it's all done. And we've now done almost all of our a to I minus val b minus plus negative 200 instruction. The only remaining thing to do is to compute 143 minus R3, and that'll finish up the work. But only the second operand in a sub can be a constant. Recall an earlier discussion where we tore apart the binary contents of a data processing ARM instruction. Only 4 bits were devoted to the first operand, just enough to specify a register, not any constant. So we're going to have a problem subtracting 143 minus R3. We want 143 to be the first operand. We could move 143 into another register and then subtract R3 from that register, but that takes an extra instruction and an extra register. Instead, line 38 uses RSB, which is like a sub, but reverses the subtraction, with the first operand subtracted from the second. As the comment indicates, the RSB instruction is designed for exactly this scenario where you need to swap the operands, and it's one of many examples of how the ARM instruction set is designed for speed. In the next segment, we'll look at the remaining few instructions, which introduce several important ideas.